previous lecture we had talked about the classical plate theory as an example of a problem which leads to a fourth order partial differential equation, okay, which we had said that if we work things out, okay, it would be this in the area A, okay, where W was a transverse deflection, D is the flexural rigidity constant, and Q is the applied distributed load on the top or bottom surfaces of the body. So this led to a variational form which was in terms of the second derivatives of W. Since it is in terms, the variational form was in terms of the second derivatives of W, so we require continuity of, because these derivatives of W have to be defined. So we need continuity of W, del W del X and del W del Y. So this is what we had required as far as continuity, and we said this would lead to just analogous to what happened in the Euler-Bernoulli beam theory in the 1D case, to C1 continuity requirement in 2 dimensions. And we had said that we look at certain ways of constructing these C1 continuous elements. So one way of doing it is, let's say I have a rectangular domain, okay, with, I will take only a few elements. So this is size A, this is size B, let this be our X and Y direction. So these are all rectangles. So what we want is at the interfaces of these rectangles with each other, including these endpoints, I should have continuity of del W del X, W and del W del Y. If I can construct basis functions which can satisfy continuity of these quantities, then we are in good shape. There were several attempts to make such elements, and various versions of triangular, here we are not considering triangular, and rectangular elements have been reported in the literature. Various types of such elements. The major problem here is to satisfy these constraints exactly, okay, in the general case. So let's take this simple case and look at an example that, let's say this is my element, rectangular element, okay. This is my rectangular element with the nodes x1 tau, y1 tau, here x2, y2, and here is x4 tau, y4 tau. So what is the basic idea in constructing such an element? You say that W as a function of x and y is equal to a0 plus a1x plus a2y plus a3x squared plus a4xy plus a5y squared, plus now I will do this a6 x cubed plus a7 x squared y plus a8 xy squared plus a9 y cubed plus, let us see, we will add some more, a10 x to the power of 4 plus a11 x cubed y plus a12 x squared y squared plus a13 x y cubed plus a14 y to the power of 4. Why did I take this whole polynomial? Because if I would like to have continuity of w, del w, del x, del w, del y at these 4 points of these 4 nodes of the element, so I will have to have w, del w, del x, del w, del y as the variables at each of these nodes. Okay. So, we will call them, I will say that w, this is essentially theta y. Theta y is the rotation about the y axis, which is given by del w del x, and theta x is rotation about the x axis. I am not bothered, I am not taking here the positive or negative signs, that one can find out. This is equal to del w del x. So, this is del w del y and this is del w del x. So, these 3 quantities are specified at each of these nodes. So, there are 12 quantities which are specified at all the 4 nodes combined for this element. So, I need to have a polynomial which has at least 12 coefficients. But here we said if you look up to the cubic in 2D, it has 10 coefficients, unknown coefficients. So, we have to do more than that. So, we go to the 4th order. But when we go to the full 4th order, there are total of 15 unknowns. So, but we need only 12 coefficients. So, what do we do? Out of the 4th order, we retain only the so called symmetric terms, this term and this term, while we drop off from the 4th order polynomial these terms. Okay. So, what we are left with is the whole cubic plus, now I will rename this, I will call it A10 here and I will call it as A11. Okay. So, this is the polynomial that we are going to fit to these values. Now, how do we do it? So, again the idea is simple, that our function w x y in the element is in terms of 12 coefficients, such that the value of this function w at the nodes x tau I, y tau I, then theta y at the node x tau I, y tau I, theta x at the node x tau I, y tau I, which we are going to call by a new name. This I am going to call as wi, this is theta yi, this is theta xi. So, this, the values of this function equals the coefficients at these nodes. So, what do we do? So, we have to have w at xi tau yi tau is equal to a naught plus a1 xi tau plus a2 yi tau plus up to a11 xi tau yi tau cubed. Similarly, theta yi at xi tau yi tau is equal to del w del x at the node xi tau yi tau. So, this would be equal to a1 plus a2 won't be there plus a2 a3 xi tau plus up to a11 yi tau cubed. Similarly, we can give what is theta xi is equal to del w del y at the node xi tau yi tau. So, this would be equal to a2 plus up to a11 into 3 xi tau yi tau squared. Okay. So, we can write the theta xi, theta yi and wi at each of these 4 nodes which have coordinates xi tau yi tau in this expanded form. How many values now we have? We have 12 values. It's a 12th order, there are 12 terms in this expression. So, now we solve for, so we can write it as this whole thing wi w1 theta y1 theta x1 then w2 theta y2 theta x2 up to all the way down to w4 theta y4 theta x4. This is equal to this matrix A into the vector of these coefficients a0 to a11. What are the entries of this matrix A? It is essentially 1 xi yi depending on the expression for theta xi, theta yi and wi in terms of the xi's and yi's. So, then implies we can get A is equal to A inverse into, or I will call it y, where this y is this vector. Okay. So, I can find the coefficients of this polynomial expression for w in terms of the values of w, theta x and theta y at the nodes, and all now we can do is essentially define the finite element solution in terms of these nodal values of w, theta xi, theta yi. Okay. So, this expression can be easily obtained. Once it is obtained, then this is known. Now, we go ahead and do the same job for all the elements, and we have the representation of the solution in the element and also globally. So, this way we can construct WFE. What will happen is WFE is non-conforming in this case. What do we mean non-conforming? Is that it does not strictly satisfy the constraint of continuity of value and derivative on each of these faces. So, on each of these edges of the element from this side and from this side. So, the two elements sharing this edge will have on this edge, as it can be shown, continuity of w and the tangential derivative of w, okay, not the normal derivative. The normal derivative here from the two sides it is not continuous. Okay. So, for example, on this face, on this edge, del w del y will not be continuous, but del w del x will be and w will be. So, this is a problem because we required our weak solution to have a minimum continuity condition of all these derivatives and w, but we are violating it. Now, the question is, because of this violation, does my finite element solution suffer? Answer is yes, but in many cases you get pretty decent solutions and this can be used. So now the question is that can we improve it? Yes, we can improve it. And where does the improvement come from? So here again is my element. Okay. Now this is the rectangular element. So here this is essentially the x direction, this is the y direction of the element. So what if in this direction, in the x direction, I took the serendipity functions as we had, not the serendipity, the Hermite cubic functions as we had created in the case of the beam analysis. Okay. So if I take this one, this is what we had as n1 Hermite cubic, okay, as a function of x. This one would be n2 Hermite cubic as a function of x. Similarly, I can create there are other Hermite cubics. This will be n3 and n4. So this will be n3 Hermite cubic as a function of x, and this will be n4 Hermite cubic as a function of x. Okay. This Hermite cubic, what does it do? If I have another element here and I have the same Hermite cubic here also, same definition, it ensures continuity of the derivative also in this direction, which is essentially the x derivative, del w del x. Similarly, I will define now the Hermite cubic with respect to y in this direction. Okay. So the Hermite cubic with respect to y would be this function. These functions. So I will call this n1 Hermite cubic with respect to y. This is n2 Hermite cubic with respect to y. This is n3 Hermite cubic with respect to y. And this is n4 Hermite cubic with respect to y. So this way, sorry, not this one will be n4. Yes. So these are our Hermite cubics. So this is n4, n3, n2, and this is n1. So we have these Hermite cubics in the x and the y direction. So what we did in the tensor product family for the quadrilaterals, same thing we can do here. How many functions we can create now by taking products of these Hermite cubics in the x and the y direction? We will create 16 functions because there are 4 in the x direction, there are 4 in the y direction. And these functions, if you remember, will now be given in terms of nodal values of some quantities. It turns out that it will be in terms of nodal values of w, del w del x, del w del y, and del 2w del x del y. So these 4 nodal values, in terms of these 4 nodal values, I can define the Hermite cubics. You see that one thing has happened. This also enforces an extra constraint that we are also asking for this cross derivative of w, that del 2w del x del y, to be also continuous in this case. But nevertheless, our basic requirement is satisfied of this w del w del x del w del y being continuous. So how can I construct these Hermite cubics? So at every node we will have, I will call it as wi. This we had said theta yi, this was theta xi, and this we will call it as kappa xy I. So essentially we will get the values, the representation of w in terms of these 4 values at a node, that is total of 16 values. Okay. Now it is very easy to construct these functions. So I will call my n1 Hermite cubic as a function of x and y will be equal to the Hermite cubic corresponding to this line and this node. It is n1 Hermite cubic due to x, and the Hermite cubic, which is 1 here, value 1 corresponding to this line, so it will be n1 Hermite cubic y. Similarly, n2 Hermite cubic xy will be equal to, let us say I will take the same value 1 here and the derivative 1 here. So, it will be n1 Hermite cubic in this direction x into let me take derivative in this direction, value in this direction. So, I will take n2 Hermite cubic with x, n1 Hermite cubic with y. Similarly, n3 Hermite cubic with respect to xy is equal to, I will have n2 n1 Hermite cubic with respect to x, n2 Hermite cubic with respect to y, okay, and n4 Hermite cubic with respect to xy becomes n2 Hermite cubic with respect to x and n2 Hermite cubic with respect to y. So, we have essentially the 2 Hermite cubics in each of these directions which are non-zero, which have some meaning here, which are non-zero at this point, okay, either in the value or in the derivative. With respect to those Hermite cubics, products of those Hermite cubics, we construct the 4 functions here. Okay. So, you see that this one n2x into n2y will correspond to this cross term, that is product of the 2 derivatives, while the value here will correspond to the n1h Hermite cubic will correspond to the value wi, and the others will correspond to the slopes in one direction or the other direction. Okay. So, I can say that this will correspond to wi, this will correspond to theta yi, this will correspond to theta xi, this will correspond to kappa xy I. So, at every node, so I can define these Hermite cubics with respect to the non-zero Hermite cubics at each of these nodes. So, I will have the n1, n2, n3, n4 here, then I will have n5, n6, n7, n8 in terms of the Hermite cubics which are active here, and so on. So, this way I can create all the 16 Hermite cubics, and now I have a so called conforming approximation over the rectangular elements. Okay. It is for you to see whether for this kind of a domain, if I make a mesh of quadrilaterals, okay, somehow I will make the mesh of quadrilaterals, something I will do here. Okay. In this mesh of quadrilaterals, whether these Hermite cubics do satisfy the continuity of the x and y derivative on these faces. Okay. If they do, then they are actually conforming in all cases. If they don't, then they are not. But for the rectangular domain, they will satisfy conforming condition. You check here. This is an assignment problem which you can work out and check. Okay. Plate theory. Since we are on the topic of plate theories that we have dealt with now, the Kirchhoff plate theory was for very, very thin plates where the shear effects could be neglected. So, while on this thing, let us go a little further. So, we can have a plate theory which is called the Reiner-Mendlin plate theory, which is an improvement over the plate theory that we have discussed, which led to the 4th order differential equation. The idea behind this plate theory is this kind of a representation of the displacement field in terms of the transverse coordinate. Okay. So, here I will have this as theta y. V x y, it should be a function of z also, z is equal to V0 xy plus z theta x, and w x y z remains w x y. So what this theory does, it assumes that E z z is still equal to 0. This means gamma x z, gamma y z are constant, while from our standard strength of materials we know that gamma x z and gamma y z is actually parabolic across the in terms of z. Okay, but nevertheless this is an approximation which is made. I am not going to delve too much into this plate theory as such, but let's bring out an important aspect of it. What happened in the case of the Kirchhoff plate theory, that we said these things were 0. Because these things were 0, this theta y and theta x came out as minus del w del x and del w del x and del w del y. Okay. Here we do not want this to happen. So these are essentially free or independent variables. So in this problem we solve for u naught. Where is u naught v naught coming from? If I have in plane loading. Okay. So u naught v naught, if I don't have in plane loading, then we can ignore these two parts, where z is with respect to again the center line of the plate. So u naught v naught w theta x and theta y, these are the 5 unknown functions that have to be solved for in order to construct the full solution. Okay. This is one feature that we have for the Reiner-Mindlin plate theory as compared to the Kirchhoff theory, where we only needed to solve for u naught, v naught and w, 3 functions. Okay, if I do this, then let's see, by now you should be able to tell me that Exx is actually equal to u naught comma x plus z theta y comma x. Eyy is equal to v naught comma y plus z theta x comma y. Okay. Ezz is equal to 0. Gamma xz is equal to w comma x plus theta y. Gamma yz is equal to w comma y plus theta x. Okay, and gamma xy is equal to u naught comma y plus v naught comma x plus z theta y comma y plus theta x comma x. Okay. So this is the state of strain at any point given in terms of u naught, v naught, theta y and theta x and w. Okay. You see that in the strain terms, the first derivatives of w, u naught, v naught and theta x, theta y are sitting. So only first derivatives. So if I now write the strain energy, that is I write the stress in terms of the strain, so the stress will also be in terms of the first derivatives of all these quantities. So the product stress into the strain, sigma xx into Exx, will be in terms of the first derivatives of u naught, v naught and so on. Okay. So the strain energy definition, as we had written, strain energy is integral over the volume of half of sigma ij Eij dV, okay, Ij going from 1 to 3. Okay, this expression would be product of at most first derivatives of u naught, v naught, w, theta x and theta y. Okay, so it's quadratic in terms of the first derivatives of all these unknown functions. Okay, so if I look at the strain energy, for the strain energy to be finite, we only want these to be defined. So we only want these first derivatives of u naught, v naught with respect to x and y, theta x, theta y and w, all with respect to x and y, to be defined. which means that here if I want to now construct a basis function to do the approximation, we need to use only C0 elements. Okay, that is, I can use the standard C0 elements that we had talked about in a very detailed way earlier when we started the two-dimensional problem. Those elements, those basis functions, like you had the linear, quadratic, cubic, triangles, the tensor product, quadrilaterals, the serendipity quadrilaterals, all those things can be used for the approximation of u0, v0, theta x, theta y and w in terms of x and y. Okay? So then this problem can be solved very easily using the machinery of the shape function generation and integration and all those things that we had developed earlier. Okay? So this way we can essentially use the tools available to us in a judicious manner. Okay? This model, it is not to say that this model will do better than the Kirchhoff plate model or it will do worse. This model has its inherent problems which can be corrected, okay, to take care of things. This one should read the books and enough of material is available. There are also higher order plate models which go beyond this expression of u in terms of z theta y, z theta x, and you add more terms in terms of higher powers of z. So you would have z squared, you will have some other quantity which is a function of x and y, plus here also z squared more. So this way you can construct so-called higher order shear deformable theories, because in those theories the shear stress or strain will be non-zero and the higher ones will also give you a non-constant shear stress. So the idea is you use sufficient number of terms to get a parabolic variation of shear, which is when you take the cubic terms. That is celebrated higher order shear deformable theory, what is known as HSDT, due to Reddy et al. J.N. Reddy and lots of other people have done this. Okay, a very good reference is on these plate theories are papers by J.N. Reddy, papers by Tarun Kant from IIT Bombay, and from Szabo, Actis and Babushka. Szabo, Actis and Babushka on a different approach to creating these plate models. Okay. So on. Okay. I will not deal with those things in detail. Now I think you are in a position to deal with all these plate models and the refinements if you need them and how to handle them. Okay. So let's go a little ahead with what we are doing. Let's now talk of a more interesting problem in common practice nowadays, because the computational tools have improved tremendously. We can get dual processor machines with very high speeds, 3 gigahertz, 3.4 gigahertz, sitting on a desktop, okay, at a very affordable price even here. So in that case, the capabilities have improved, and because of that our desire to do more refined modeling of the physical problems. Okay, if you see the beams, the plates, the bars, these are all idealizations of a 3D situation. So why not do three-dimensional analysis? So I'll briefly touch upon three-dimensional analysis and how it is done. The language, the procedures are direct analogous extensions of what we had in the 1 and 2 dimensional cases. So now let's say that here we have a 3-dimensional domain. I will take a cubical domain for simplicity. Okay, let's say the volume of the domain is V and the surface is given as delta V. Okay, over this domain I would like to find the response of this structure when, let's say, on this face I am going to fix my displacement, completely fix this face, and on this face partially I want to apply a transverse load. You can see that this looks like the bending problem. Okay. Now, if it is a long slender member, you will see that what you get out of the beam analysis will be close. If it is flat and both dimensions are similar, plate analysis will do a good job, but that is for you to see. But here we would like to do an honest three-dimensional analysis where the load is applied here. Okay. Then how do we solve this problem? First of all, we are talking of 3D elasticity as an example of a 3D problem. And for 3D elasticity, we would like to develop the variational formulation and then suggest how to go and create the basis functions or the shape functions which can be used to solve the problem. So, okay, some things that we should keep in mind before we proceed. You see that here I have deliberately applied the load in only part of the domain. Okay. This we should keep in mind, and the boundaries now of this three-dimensional domain are surfaces. That also we should remember. Okay. They will have surfaces, surfaces will have edges and the corners. So, these are faces, these are edges and these are corners. So, let us write the 3D equation of equilibrium for the theory of elasticity. Sigma xx comma x, okay, plus sigma xy comma y plus sigma xz comma z plus fx is equal to 0. Similarly, I will have sigma xy comma x plus sigma yy comma y plus sigma yz comma z plus fy is equal to 0. Here I am assuming that the stress tensor is symmetric, that is sigma xz is equal to sigma yz, sigma xy is equal to sigma yx and so on. And sigma xz comma x plus sigma yz comma y plus sigma zz comma z plus fz is equal to 0. Okay. So, now this quantity I am going to call as my R1, this is my R2, this is my R3. That is, these are components of the residue vector. Okay. So, now as we had done in the two-dimensional case, let us take W with components W1, W2, W3 as an admissible displacement. This is an admissible displacement, virtual displacement, while we will have the vector u with components u1, u2, u3, where each of these components u1, u2, u3, w1, w2, w3 are functions of x, y, z. This is the unknown displacement field. Okay. So, what we had done earlier, we had said that we will take the weighted residual formulation, that is, we will take the volume, take R dotted with W and integrate it over the volume. Because R was 0, this will come out to be 0, okay, against any, where W is any admissible virtual displacement. Admissible means it should satisfy the geometric constraints wherever U is specified. Okay. So, from our, let me jump the gun and say what we want our W to do in the standard situation. We have not yet done integration by parts, we will do it, is that W should satisfy the constraints, there is this one and this one. Okay. But let us see what happens. Then out of this I am not going to write the long expression, I will do integration by parts once. Okay. By doing integration by parts, I will end up getting this expression sigma xx into Exx due to W plus sigma yy into Eyy due to W plus sigma zz into Ezz due to W plus sigma xz gamma xz due to W plus sigma yz gamma yz due to W plus sigma xy gamma xy due to W. This whole thing dV will be equal to here F1 W1 plus F2 W2 plus F3 W3 plus integral over delta V. I will explain what is this. Traction vector T dotted with W dA. So this is what we mean by this is that traction T. What is traction T given as? If you remember, the T1 is equal to sigma xx nx plus sigma xy ny plus sigma xz nz. T2, that is the component of the traction vector in the x direction. T2 is the component of the traction vector in the y direction. This will be nx plus sigma yy ny plus sigma yz nz, and T3 is equal to sigma xz nx plus sigma yz ny plus sigma zz nz. Okay. This is standard. If you do this integration by parts and use the Gauss-Green divergence theorem, you will get this in terms of that expression. Okay. So we will get this. Now you see what are these nx, ny, nz? These are the components of the unit outward normal on the area. So here let us come back to our problem. The unit outward normal is the vector n here. In this case, since these are all parallel, n will be equal to 0I plus 0j plus k. So it has only the component nz which is equal to 1 on this face. Okay. But in the general face, general aligned face, you will have all the three components nx, ny and nz. Okay. You will have all the components of n. So now if you see that where does the t become non-zero? Only on this part of the boundary area. Okay. And in this case you see that your T1 is 0 because I have drawn these as vertical forces. T2 is 0. Here T is equal to vector T is equal to minus T3 T3 E3, unit vector in the third direction. Okay. So I will put this expression for the T in the expression here, and I will essentially go ahead from here. Now again coming back to what we had drawn there, when now I have done the weak formulation, the one I had written, the last expression is the weak formulation. The weak formulation tells us that sigma xx due to the u into Exx due to the w and so on have to be defined in order for this integral on the left hand side to be finite, which means sigma xx is in terms of the first derivative of u and first derivative of v and so on. So similarly for Ex, Ey and so on, these are all in terms of the first derivatives of u, v and w with respect to x, y, z. Okay, u and w with respect to x, y, z. So our weak form now requires only the first derivatives of the vector u and vector v and vector w to be defined. Okay, which means that in this case we need, with respect to what we have done, as far as the approximation is concerned, we need to construct a C0 approximation in 3 dimensions. That is, we only want the value of these functions u1, u2, u3, and similarly for the test function w1, w2, w3, which is the virtual displacement, to be continuous. Derivatives need only be defined. So how do we define now continuous shape functions? First of all, how do we discretize the domain? Okay. So let us take our domain of the previous figure and let us make a mesh here. So how will I make the mesh? For the mesh, I have to honor the boundaries of the load profile, boundaries of material differences. So wherever my material has a change, that boundary should be will have the nodes and the edges and the vertices, nodes and faces of elements sitting there. What kind of element should I make? So in this case, life is a little simpler. So I will make this kind of a partition. Very simple partition, you see. Here I will make it with a different color so that you can see the effect. Okay. Similarly, in the third direction, I will make the partitions like this. So, if you see what we have done, we have constructed elements which are actually cubical in shape. Okay, elements which are cubical in shapes. Well, the sides could have different lengths. So these are called, in the language of finite elements, brick elements. There are other types of elements we can make, but I am not going to discuss them here. So this is a brick element. So let's do a very simple job of constructing a finite element basis functions, or here we will only concentrate on the element. So the shape functions which are C0 continuous now for the brick element. So let's say my coordinate system is, this is x, this is y, this is z. So x, y and z. I'll call this for the element, let's say this is my generic element. This is my generic element tau. This is the node 1 of the element tau, node 2, node 3, node 4, node 5, 6, 7 and 8. So this will have coordinates x1 tau, y1 tau and z1 tau. Similarly, all the other nodes. So the mapping, now we will take this and I am going to go straight away to the master element. This will map to a master element which is a master cube. Okay. So we make a master cube like this. This will be my psi direction, this will be my eta direction and this will be my zeta direction, such that this point is at psi eta zeta minus 1. This point is at psi zeta eta 1. Just like we had the 1D element, master element, then the 2D master element, now we have the 3D master element. So this point will have essentially psi, your zeta will be 1, psi will be, sorry I have made a mistake. So this will be, psi will be plus 1, zeta will be minus 1, eta will be minus 1, zeta will be minus 1. So this will be plus 1. So here my psi will be minus 1, zeta will be, psi will be minus 1, zeta will be minus 1, eta will be minus 1 and zeta will be plus 1. So this way we can construct the 4 nodes. Now we want to define the basis functions or the shape functions with respect to these master nodes, okay, such that the shape function which is defined with respect to this node is 1 here, 0 at all other nodes, 0 at all other master nodes. How do we define? Very simple. We now take tensor product of the 1D shape functions that we had created, C0 shape functions in the 3 direction. So my n1 here, n1 hat as a function of psi eta zeta will be equal to n1 with respect to psi, okay, sorry, it will be n2 with respect to psi, n1 double hat with respect to eta, n1 double hat with respect to zeta, and so on. Okay, so I will take the tensor product as if this is my psi direction, -1 to +1. This is my eta direction from -1 to +1, and this is my zeta direction from -1 to +1. So my confusion was because my psi direction is positive in this direction. Okay, so here this shape function was non-zero with respect to psi, with respect to eta, this guy will be non-zero, and with respect to zeta, this guy will be non-zero. So for the zeta, this is the first one, this is n1 double hat eta, this is n2 double hat psi, this is n1 double hat zeta. So in terms of these 1D shape functions, we can construct these 3D shape functions, and you see there will be 8 of them. They will satisfy completeness, linear independence, and all those properties. This way, now putting them together, we can construct the global basis functions. Remember that the basis functions will be by piecing together these shape functions from all the elements which share this node, okay, and then we can construct the 3-dimensional finite element solution for each of these components u1, u2, and u3. Solve using the weak formulation that we have done, and we are now in a position to solve the 3-dimensional problem. But remember that here applying the boundary conditions is a bit tricky, because we have to do now integral of the given loads over the area of the faces. Okay. In general, for the general 3-dimensional domains, defining the domain, meshing the surface of the domain, meshing the interior of the domain is not such an easy job, and for that you need sophisticated mesh generators which have to be used to construct the mesh on the surface now of the outer surface and the internal volume. With this, I will stop my brief foray into the 3-dimensional problem, before which we have discussed the plate problem, which was essentially in between the 2D problem and the 3D problem. Before that, we talked of the honest 2D problem, which is the planar stress problem and planar strain problem, as well as the 1-dimensional heat conduction problem. Next, what we are going to do is we are going to now develop methods for a different class of problems which relate to eigenvalue problems at the continuum level. Okay. For example, the free vibration analysis or the buckling analysis. How do we solve those problems using the finite element